Heap data structure, also called heap tree, is a data structure where root element is either always smaller or bigger than its children. Say this is a tree, binary tree, and we have element here 20, and the childrens are 10 and 12. Here the root element or the parent of 10 and 12 is bigger than 20. And one more example is, let's say here we have 10 and 20 this side and 12 this side. Then here 10 is smaller than both the children's, and both these structures are called, both the trees are called heap tree. Heap tree. This one is called a max heap tree. When a node is bigger than both its children, then it is a max heap tree. If the parent is smaller than both the children's, then it is known as the mean heap tree. Mean heap tree. So in this video, we'll talk about the heap tree or heap data structure. Also, we'll see how to add element or insert element in the heap tree, and also delete an element from the heap tree. Suppose we have a set of elements such as 10, 15, 9, 8, 11, and 4, and a heap need to be created. First of all, a heap or a heap tree either can be a max heap or a mean heap. If it is a max heap, if it is a max heap, then the root element would be greater than both the left and right children. Unlike BST, there is no such restriction. Let's say here we have 10 and we have 7 and we have 6. This is a heap tree because the root element is bigger than both the children. In BST, what we have, the element in the left side of the root should be smaller than the root element, and on the right hand side should be greater than the root element. That restriction is not not available in the heap tree. So from the given set of elements, we wanted to construct one max heap tree or max heap. Let's see how that can be that we can do. The heap tree should be constructed as a complete tree, complete binary tree, where the first element will be root. So this is root, 10 will be root, and 15 will come as a left children. And then we will compare, because in the max heap, root should have the maximum element. Root should be maximum. So but however here 15 is greater than 10, so we will swap these two elements. So we will reconstruct it as 15 will go there and 10 will come here. So the tree will be, new tree will be 15 as a root and 10 as the children. Then we will add, these two are added. Now 9 will go to the right child, because we need to construct the complete tree. And complete tree, in a complete binary tree, first we need to fill the left element, then we will go to the right element. Once this level is filled, then we will add element in the next level. So 9 will come here. We'll compare this 9 with the root, but 9 is smaller than the root element, so no need to change any element. Then we will add 8. 8 will come as a left children of 10, and we'll compare with this its parent 10. It is 10 is greater than 8, so no need to change. Then we will enter 11. 11 will come as a right children of 10. And then when we compare this 10 and 11, we can see the 10 is smaller than 11. That's why 10 and 11 to be interchanged. So 15 is there in the root, and 10, in place of 10 we will put 11, and 8 will be in their its original place, and 10 will move to the place of 11 will move to the place of 10. So these two elements are interchanged. Now add element 4. Element 4 to be added in the left of 9, because left and right child of 11 is filled. Now we have to fill the left and right child of 9. So 4 will be placed here, and then we'll compare 4 with 9. 4 and 9, 9 is greater than 4. That's why there is no need to change these values, 9 and 4. So 4 will be placed as a left child of the element 9. So this is the tree constructed from the given set of elements. This is a max heap tree. Max heap. This max heap is a graphical representation of all the nodes, which is in max heap format, or graphical representation of the max heap tree. However, while implementing this max heap in a program, we make use of the arrays. So we will use an array to represent this max heap. Let's see how we can do that. Moreover, here we need to keep it in mind that there are 6 elements in the heap tree. So 6 is the length of the heap tree. We need 6 elements, an array of 6 location to store these elements of the heap tree. So let's create these 6 elements, 1, 2, 3, 4, 5 and 6, and let's number them as 1, 2, 3, 4, 5 and 6. Now this is our heap tree. We need to represent in the form of array. So 15, which is a root of the tree, will come in the first location. Then its children 11 and 9 will come. 11 left child will come first, then right child. Then we'll go to the next level. We'll explore 11. The children of 11 is 8 and 10. Then 8 and 10 will come. And after that, we'll go to the element 9. That is right child of 15. And then we'll go to explore 9, and in 9 we have only one element 4 in the left side, so 4 will come in position 6. This is a complete binary tree, as I have stated earlier also. This is a complete binary tree. That's why all the locations in the array will be filled without any gap. And moreover, with respect to a complete binary tree, for any element I, if I want to find its left children will be in position 2 into I, and the right element will be in 2 into I plus 1 position. For example, if I consider 11, the position of 11 is 2, position of 11 is 2, position of 15 is 1, position of 9 is 3. That way we will go on, and this is 4, this is 5 and this is 6. Now if I consider 11, the position of 11 is 2, its left children is in 2 into 2, which is equals to 4, and right children will be 2 into 2 plus 1, which is equals to 5. So 8 is located in 4 and 10 is located in 5. Similarly, if I see 9, element 9, it is in position 3, so its left children will be in 2 into 3, which is equals to 6, and position 6 is the left children of 9. Similarly, if I want to see the root of any element I, any element position I, if I want to see the root or want to retrieve the root, then it is given by I by 2 and floor, or the floor of I and 2. For example, if I consider element 10, location of I, 10 is 5 by 2, which is equals to the floor of 2.5 is equals to 2, and that's why in location 2 we can find the parent of 10. So this method is used in order to create a heap tree, or in order to insert element in the heap tree, or delete element from the heap tree. Next we will see how to add element or insert a new element, insert a new element in a heap tree, and how to delete an element in a heap tree. This is our existing heap tree and we want to insert an element. Let's say we want to insert element say 20 in the heap tree. So these are the elements. 15 is here, 15, 11, 9, 8, 10 and 4, and this location is blank. We need to insert 20. So this location is free, this location is free, or here we will insert the element in this location. If I insert this element here, then actually in the tree it will come in this location. This is the new location of 20. But however, if I look at the construction of the binary heap tree, we can see this node 20 is greater than 9, so that's why this is no longer a heap tree or max heap tree. So we are supposed to reconstruct that max heap. So what we will do, we'll compare 20 with 9, and 20 will move here and 9 will come here. Then again we'll compare this 9 with its root, and then 20 is again greater than 15, that's why 15 will come here and 20 will go there. So newly constructed tree will be, heap tree will be 20, then 11, 8, then 15 will come here, 15, 4, then this is 9, and the children of 11 is 10. And if I number these elements, this is 1, this is 2, this is 3, 3, this is 4, 5, 6 and 7. So now this tree will be now compared, and if I wanted to compare in the program, what we will do, this is the element 7. I will compare 7 with its parent, floor of 7 by 2, which is equals to 3. That means I will compare 20 with 3, 20 with 3. Since 20 is greater than 9, that's why we will exchange 20 and 9. 20 will come here and 9 will go here. Then again 20 will be compared with its parent, that is 3 divided by 2. Floor of 3 divided by 2 is 1. So we'll compare with this 15 and we will exchange this value. 15 will go here and 20 will go here. So the new array will be of the will be 20, then 11, then 15, then 8, 10, 4 and 20. So 1, 2, 3, 4, 5, 6 and 7. So this is the new tree after adding the element 20. If I look at here, 15 is greater than 4 and 9, 11 is greater than 8 and 10, and 20 is greater than 11 and 50. This is once again a max heap tree, max heap. So this is the way how we can construct the heap tree and insert new element in the heap tree. So here, in order to insert an element, how much time, what is the time complexity of this insertion algorithm? If I look at this one, we need to compare the newly inserted element 20 two times. One is with its parent, this is the node and its parent. That parent again need to be compared with its parent. That's why two comparisons are required. Basically, if I look at the tree, then the number of comparisons is equals to the height of the tree, and the height of the tree in complete binary tree, if there are n number of elements, then the height of the complete binary tree is log of n. That's why the time complexity of inserting an element in a heap tree is equals to theta of log of n. Next, let's see how to delete an element from the heap tree. So this is the given tree and we wanted to delete an delete an element, delete an element. And here the important point is, whenever we delete an element, we always delete the root element. Root element, that is the purpose of creating a heap or max heap tree. Whenever there is a need of the maximum element, we delete the root of the tree and we get the maximum. So when we'll delete, that means we'll delete the root element. Now if I delete the root element, if this one is deleted, then this is empty, but we cannot keep this one empty. What we need to do, we need to copy the rightmost children to the root. So 9 will be copied here. So newly constructed, this will be deleted now. Newly constructed tree will be 9 will come here, 11, then this side 15, then 8, then 10, and this is 4. But however, if I see 4 is smaller than 15, that is 15 is greater than 4, that is fine. 8, 10 and 11 is greater than both the children, that is fine. But however, if I go to the root 9, then 11, 9 and 15, out of these two, 9 is not the maximum. That is why it violates the rule of max heap tree. We need to rearrange elements, mainly the element 9 need to be replaced in order to make it heap tree. And what we will do, first we'll see what is the position of 9. Current position of 9 is 1. We will find out of left and right children of 9. So following the complete tree implementation, the left child of 9 will be in 2 into 1, which is equals to 2, and right child of 9 will be 2 into 1 plus 1, which is equals to 3. That means 2 and 3 are the left and right child respectively. So we need to now compare the left and right children. Here 11, and out of 11 and 15, these are two left and right children of 9. 11 is smaller than 15, that is 15 is greater than 11. That's why we need to exchange this element 15 with the element 9, 15 and 9, that is bigger of this left and right child, need to be interchanged with the root element or the parent element. So here 15 and 9 will be exchanged. So 15 will come here and 9 will come in this location. So if I again reconstruct the tree, it will be 15 here, 11, then 3, sorry 9, it is 9, then in this side it is 8, 10 and 4. Now this tree is a heap tree, max heap tree. So we can see that here we have deleted element 20 from the existing tree, and 20 once deleted, that location is replaced by the rightmost element. Rightmost in the sense that here we have the, this is, we are, I'm not saying that it is left or right child, but I'm telling that is the rightmost element. Rightmost element means this is the rightmost element here, provided once in this tree, if I once we delete that, 20 will be, first of all 20 will be replaced by the rightmost element, it will go to the root. Then after that we will make this will violate, this may violate the principles of heap tree. So we'll rearrange elements, that is also known as heapify. We will rearrange all the elements to make it a heap tree. Then now let us suppose that we wanted to delete one more element. This time the top element or the root element is 15. So 15 will be deleted. 15 will be deleted. So in order to fill this place, what we'll do, we'll go to the tree and we'll take the rightmost element. In this case, rightmost, I mean to say this element, because if I read it from this side, 1, 2, 3, 4, 5 and 6, this is rightmost element, and here also in the array it will be the rightmost element. That 4 will be deleted, 4 will be replaced, I mean 4 will be shifted to root, and then again it violates the principles of max heap. So we need to again rearrange the element. Unlike the insertion element, in the insertion element what we did, we compare the element, a children is compared with the root or parent, a children is compared with the parent, then if necessary we exchange the data. Again that element is compared with its parent, then we exchange if it is necessary. But in this case what we are doing, we are taking the root element and we are exchanging it with the bigger of its children. So in insertion of element, we compare from the leaf node towards the root. On the other hand, while deleting, we compare the element from the root towards the leaf node. So that is one of the difference between insertion and deletion. The time complexity of deleting an element is order of 1 because we always delete the element from the root. However, after deleting the element, we need to use the apply the heapify method, and that heapify will take the number of comparisons which is equals to order of log of n. And this is the way how we can delete an element from the heap tree. This tree we have discussed is a max heap, and similarly we can do the same for the mean heap as well. In case of mean heap, the parent element is always smaller than its children, both the children's. If this condition is satisfied, then this is considered as mean heap. And in case of mean heap, if we delete an element, we delete always the root, and it gives the minimum element of the tree.